Hello everyone, welcome to the LeetCode Data. We'll work on LeetCode Problem 153. The goal here is to find the minimum element in a sorted array that has been rotated. Also given that all elements are unique and the array is not empty. We have to return the minimum element in O of log n time complexity. The array is rotated means that the array was sorted in ascending order. Then some elements were moved from the front to the back. For example, the array 3, 4, 5, 1, 2 is a rotated version of 1, 2, 3, 4, 5. Here the end of the array is rotated, that is 3, 4, 5 were moved to the front. Right out of the gate we can see it's a sorted array and requires log n time complexity. That indicates towards the binary search as the optimum solution. Before getting into binary search, let's think about the brute force solution to better understand the problem. We can simply iterate through the arrays and find the minimum element using the built-in min function in Python. Under the hood, it will iterate through the array and find the minimum element. As you can see from the result, the built-in min function in Python is highly optimized, as is written in C, and works well for the small arrays. But this will take O of n time complexity, which is not what we want. Though before going to the binary search, we can actually do better with O of n time complexity. As we know that the array is sorted and rotated, we can take advantage of that. In a rotated array, there is exactly one cliff. One place where a bigger number dropped to a smaller one. This is a cliff where our minimum exists. As we can see on the screen, 7 drops to 1, that's our cliff, and 1 is our minimum. Let us implement this solution as well. In the beginning, we'll start with the no rotation check. If the first step is lower than the last one, we are on the normal uphill trail. There is no cliff. The first element is the minimum. This is our O1 early exit. But if first is greater than the last, we know there is a cliff somewhere. We walk along the trail checking each step. The moment we find a drop to a cliff, and the element there at the bottom is our minimum. This also works well with the small arrays or where rotation is small or near the beginning. Now the time has come for the star of the show, the binary search solution. The idea is to use binary search to find the cliff. We'll start with the 2 pointers, left and right, at the beginning and end of the array. We will then calculate the middle index and check if the middle element is greater than the right element. If it is, then we know that the minimum element has to be in the right half of the array. So we move the left pointer to the middle index plus 1. If it is not, then we know that the minimum element is in the left half of the array. So we move the right pointer to the middle index. We will continue this process until we find the minimum element. Here you can see there is a cliff at index 2. Mid is at index 3. And because mid is greater than the right, we know for sure that the minimum element is in the left half of the array. Similarly, if min is now at index 5 and mid is at index 3, and because mid is less than the right, we know for sure that the minimum element is in the right half of the array. Let's go through one more example. Here we have array 3, 4, 5, 1, 2. We start with left equal to 0, right equal to 4, and our mid would be 2. That we check if the mid element, that is 5, is greater than the right element 2. If it is, we move the left pointer to the middle index plus 1, which is 3. Now we have left equal to 3, right equal to 4. We recalculate middle index, that would be 3 plus 4 divided by 2. In integer, that value would be index 3. We check if the middle element 1 is greater than the right element 2. It is not, so we move the right pointer to the middle index, which is 3. Now we have left equal to 3 and right equal to 3. Left and right will always converge to the minimum element in this algorithm. Now let's go to one more example with array 11, 13, 15 and 17. We start with left index equal to 0, right index to 3. We calculate middle index to 1. We check if middle index element 13 is greater than the right element 17. It is not, so we move the right pointer to the middle index, which is 1. Now we have left index equal to 0, right index equal to 1. We calculated the middle index to 0. We check if the middle element 11 is greater than the right element 13. It is not, so we move the right pointer to the middle index, which is 0. Here now again we have left equal to 0, right equal to 0, and index 0 is our middle point, is our minimum point here. Let's walk through the code for this elegant binary search solution. We initialize 2 pointers, left at index 0, right at the last index. These represent our current search window. The minimum element is guaranteed to be somewhere between these bounds. We continue searching while left is less than the right. When they meet, we have found our answer. Now it's less than, not less than equal to. This prevents infinite loop. Calculate the middle index using integer division. This is our prop point, where we will make our decision about which half to search next. This is the algorithmic call logic. If the middle element is less than or equal to the right element, it means the right portion is properly sorted. Therefore, the minimum must be at mid or somewhere to its left. We set mid equal to right to search the left half, keeping mid as a candidate. If nums mid greater than the nums right, there is a rotation point cliff somewhere between mid and right. The minimum must be in the right half. We set left equal to mid plus 1 because mid itself cannot be the minimum. It's larger than at least one element to its right. When the loop exists, left equals right, pointing to the minimum element. We return nums left. Throughout the execution, we maintain the invariant. The minimum is always within left and right. Each iteration eliminates roughly half of the remaining elements while preserving the invariant. Thank you for staying with me throughout this explanation. If you have any questions or suggestions, please feel free to leave a comment below. If you enjoyed this video, please give it a thumbs up and subscribe to the channel for more content like this.